Welcome everybody to this lecture on linear superresolution. So already on this title slide you see some examples of what superresolution can image. So on the left hand side it's very small organelles called protosomes in a cell. In the middle here you see Drosophila, a Drosophila embryo developing, so you see the cell division. And on the right-hand side, you see a more large-scale image of a head of a Drosophila fruit fly. So these are these tiny flies that, especially in the summer, you can sometimes see around your apple or something like this. Okay, so here comes a little overview on superresolution. I'm going to talk first, give an introduction on why do we need resolution, something about Abbe's limit that you've already probably heard something about, a quick introduction into Fourier space because that's important to understand structured illumination sim. And then finally, I'm going to talk about structured illumination. So we're starting with why resolution. So what you see here is a zoom into the university main building, UHG in Jena. And it sort of is meant to demonstrate that when you have a higher resolution, here visualized by being closer, you can actually see more, and that's pretty clear. So at the moment you have no idea where even Jena is, and while you're zooming in you get more and more details. And of course that's what we are interested in when we are doing super resolution imaging as well. So this is a nice little trick to motivate super resolution. So when you're seeing this on a big monitor right now, then you probably will recognize a famous face. Yes, you're right, this is Albert Einstein. However, when you have less resolution, so if you go now far away, or you just put your eye close together, you're probably going to see something different. Well, I'm going to help you, make it a little smaller for you. So what are you seeing now? Presumably you're seeing Marilyn Monroe. So this is exactly the same image, but presented to you by the virtue of your eye in different resolutions. And as you see very different, you have a very different interpretation. So in biology, there are similar phenomena when it comes to particular problems. When you have a higher resolution, you can see more details, and that might actually change your interpretation. So, for example, at low resolution, you will just see that two particular dyes, maybe a red and a green dye, are both localizing to the same type of cells. So that's great. But then you zoom in, you get a better resolution in the end. So it's not just about the zooming, it's the resolution. And then you can suddenly resolve that they are both in the mitochondria of these cells. You can still not separate them somehow, but they're in the mitochondria. When you then get super resolution images at maybe 100 nanometer resolution, you can suddenly start to see that one dye, let's say the red dye, is in the membrane, whereas the green dye would localize to the lumen of the mitochondria. So that's a similar phenomenon. When you have high enough resolution, you can suddenly discern a difference, and that changes massively your interpretation, your molecular interpretation. What does a microscope do? Well, this is a very simplified picture, but mathematically describing quite well what a microscope does. It's a convolution operation of the object with the point spread function. And the point spread function can be represented as a brush. So you see here the brush, the point spread function, and on the left-hand side, the object. And how would the image now look like? Well, as a convolution, on the right-hand side, you now see how such a convolved image looks like. So convolution, as written here, a fairly complex mathematical integral operation, is simply a mathematical representation of drawing with a brush. So you see the object on the left gets drawn with a fluffy brush. And of course, if you want a sharper image, then it's all about the quality of the brush. If you, rather than taking a fluffy brush, you take a pencil, like symbolized here, when you draw now the object with the new brush, the high resolution brush, so to say, you get a high resolution image and you can discern much more detail. So that's why this operation, or the technology of getting better brushes, you can also call point spread function engineering. It's about engineering better point spread functions that are sharper. But of course, there's lots of discussion what you call sharp, and this will be one of the next topics, i.e. Abbe's resolution. So this is about Abbe's resolution limit. In this slide, you see interfering water waves. So on the right-hand side here, you see a mechanism that basically wiggles the surface of the water and in a regular fashion, and then you see that actually sinusoidal waves are sort of emerging as elementary waves from these 2 points where the water surface is disturbed, and their interference then gives rise to particular areas where the water still remains constant and is not moving. That are these sort of hyperbolic curves that you see here, whereas at other places like here you have a lot of moving waves. So in an analogy to light wave, these parts that are very much perturbed, where the waves are running along, is an area of high intensity, where something like this would be a dark fringe where it would be completely black and you wouldn't see anything. So remember that the eye is not sensitive to the amplitude that you see here as brightness, but it's actually just the amount of wiggliness, so to say, that is the intensity. That is what the eye can detect. So the amount of perturbation of this water surface in this analogy. I've sort of made a little simulation that you can see here. And you see that when a plane wave, as symbolized here on the left-hand side, when this plane wave hits a tiny little pinhole, you get a circular emergent wave. And I guess this sort of observation is what led Huygens to this picture of these elementary waves that can be superimposed to even explain more complex phenomena. Here is such a more complex phenomenon. Now we have many holes, as seen here, and here, and here, and here, and here, many of them. And when these many circular waves that emerge from each of these holes, when they superimpose, you first get some sort of area where it seems to be pretty complex, but eventually in this simulation you see how there's basically 3 different waves emerging. One is more or less the unperturbed original wave that went to these holes. And this is called the 0 order, the direct transmission. However, there's also another wave that goes into the diagonal here and another wave here, which of course are the plus and minus first diffraction order. And if you want to work out what is the this direction where the first order emerges, you have to basically realize that there's always one full wavelength discrepancy in this diagonal direction between one hole and the next one. And that's why, again, you get constructive interference of these elementary waves. So here, I would denote as central head-on, and here, Abbe's trick is to now not illuminate the grating centrally, head-on, but diagonally off axis. So this is called oblique illumination. And in this situation, you see that we have this distance lambda over well, this can be a lambda over n, and therefore this distance here is only lambda over 2n. And so then we have sine alpha is lambda over 2n, and that gives us Abbe's famous, that is written in stone here. So here you see the equation, and here you see it written down, and I'm going to write down, of course, what these things mean again for you to be absolutely sure. So D is the minimal grating constant, so that's the pitch between the beginning of one hole and the next one, or for what it matters also any sort of phase changes in the object. if they are periodic. And it turns out you will understand later why this periodic analysis also applies to anything really. Right. This is the wavelengths of light in vacuum, whereas divided by n gives you the wavelengths of light in the medium, so lambda over n. Then we have the factor of 2, and we have sine alpha, which was alpha, the half opening angle of the objective, which is really measured as sort of what would correspond to the ray that just makes it through the backfocal stop aperture. But the interesting bit here is you should also realize it doesn't help to make alpha bigger than 90 degrees. You see, sine alpha would reach 1 if we have the perfect objective, so to say, but even then there's lambda over n, which lambda over 2n, which limits us in resolution. So since normally for high NA objectives, alpha is something like 70 degrees, you barely gain any extra resolution by getting a better objective than such a 1.4 NA or so. So that doesn't really make a difference. At that point, it's more important to think about other refractive indices or, of course, shorter wavelengths, X-ray microscopy, and so on. Right. So here, remember again this convolution phenomenon that we had before. So painting with a brush convolution describes microscopic imaging. This is particularly true for these microscope systems that are designed according to the Abbe sign condition. So now you might say, well, this is all fine, but what the heck has Abbe's analysis of transmitted light microscopy to do with fluorescence microscopy? And if you think a little bit, you can actually realize a particular similarity, which is the following. You see that if a fluorophore sits here, the fluorophore would emit a circular wave, but out of the circular wave can be decomposed into lots of plane wave components. And now you can ask yourself, each of these, well, they all interfere with each other, and they give you, if you have two plane waves interfering, they give you always a sinusoidal sort of pattern of amplitude that would then contribute by adding up all the amplitudes to the final point spread function. So we're really interested now in the image of a single point object. And the interesting bit is if you think about what is the finest possible contribution that rays here or plane waves can do, then you find that it is actually the same two rays. In the original Abbe picture, the undiffracted zero order would just about go onto one side of the objective, make it through the aperture, and contribute to the interference with the first order, and here only the plus first order, that would make it through just about the other side of the objective and interfere with the zero order. And therefore, it gives rise to a sinusoidal component, which again, in its sum with lots of other sinusoidal components, is part of the point spread function. Now, the interesting bit is that these two rays are exactly the same two rays as in Abbe's picture that form the highest frequency part of the point spread function. And because of the convolution theorem, the point spread function can be decomposed into sine waves and is easily describable by its Fourier transform, which is the optical transfer function. And the finest frequency component in the point spread function means that this is the highest frequency in Fourier space, which is still non-zero for the optical transfer function. So to understand this a little bit better, I will now go a little bit into Fourier space. So this is what I just tried to explain. You see the optical transfer function being the Fourier transform of the full point spread function, the incoherent intensity point spread function, Fourier transformed. And you see that this has a fixed limit, which is the highest possible frequency which is contained in it, i.e. the interference of the same two waves, and therefore also Abbe's limit written down in reciprocal space, which is basically just 1 over d or 2 pi over d, depending on how you are, which coordinate you're writing down for spatial frequency. So remember drawing the convolution in real space, that's fairly complicated, becomes in Fourier space, due to the convolution theorem, a very simple multiplication of two functions, the Fourier transform of the object, meaning you decompose any object into its sinusoidal parts, and you decompose the point spread function into the sinusoidal parts. You Fourier transform the object, and you Fourier transform the point spread function, yielding the optical transfer function OTF. And then you're multiplying the two together, so your object gets modulated by the transfer function. Therefore, the name, for example, the transfer function has a value of 0.1 here. It means that this original object component, whatever it may be, will be multiplied by 10%, by 0.1, and therefore dimmed down, transferred to a lesser degree compared, for example, to the zero frequency. So of course, at the Abbe limit, the transfer becomes 0, and therefore all information is deleted for higher frequencies. So that's why I really love Abbe's limit and Abbe's explanation of resolution, because it is not a thing that is relative and can be changed by messing around with things. It's a pretty absolute limit that says to here and no more. After it, there's zero information transfer. So to regain more information out here, you need to make certain assumptions on your object, and then you can do sometimes some things, but usually you can't. Or of course you can have to come up with other ideas, and that's of course part of the super resolution imaging. So once again, the finest oscillation in a point spread function means the finest detail in an image that can be transferred. So we need to now understand a little bit better Fourier space. What is Fourier space? So I start with a very simplistic explanation that of course doesn't cover all the mathematics, and you probably had much better and more in detail explanations, but it's still good to remind you what we are looking at so that you get a little bit of feeling of Fourier space. So what you see here is how a signal, in this case a periodic signal, looks like in real space. So it's a rectangular function in this example. And now we are basically starting to fit this function with different approximations of what is called spatial frequencies. So oscillations over space, i.e. wavy things. So we start with the simplest oscillation, which is a spatial frequency of 0, which actually is just a constant. So you see that the 0 frequency always corresponds to the constant, or in other words, to the mean value of your signal here. So remember, 0 frequency, the strength of your sort of graph at 0 frequency, so in other words, the Fourier transform at 0 frequency corresponds to the mean value of your signal. Of course, there might be, depending on how you define Fourier transformations, there might be factors, constant factors to it, but I'm just neglecting them right now. So then, of course, the basis frequency, or sometimes called ground frequency, would be something like this. So our very first approximation is the sum of a constant plus a sine wave with exactly the same period that our grating has here, or our rectangular periodicity. So that looks pretty good. But now we need to try to get better approximations. So can we add higher harmonics to this to get a better representation? Well, it turns out the next harmonic would be the second harmonic, as you see here. So that makes 2 oscillations per original period per basis frequency. And if we try to add that, it would be a bad decision, because even though we would be sort of making it better here, we would actually make our signal worse here. So it turns out that this gives you 0. However, the third harmonic is actually a pretty good one. As you see, it makes it better here, it makes it better here, and it makes it better here. So therefore, we add it. And then you can go on and on and on and add higher frequencies. In this particular case, you will find that only the odd harmonics will contribute, and you can get better and better approximations to the original signal by adding sine components. So this is to motivate that a periodic signal can be decomposed into sine waves. And what you see here is the same thing with a few higher orders. So you see here, the more of these sine waves you're adding up, the more detailed can you reconstruct your original sample. And this idea was invented by Jean-Baptiste Fourier, and you see a picture of him here, and we will Fourier transform him a little later. But before we do so, I want to show you a neat experiment. So what I've done here is I've printed certain sinusoidal patterns here. And they are, of course, intensity patterns rather than amplitude patterns, but it serves as an analogy. So you see, this is a coarse wave and then a higher harmonic, for example, third harmonic, fifth harmonic. And if I print some of them, and now you take a cylinder lens that you're basically placing the cylinder in this form here. So a rod oriented horizontally, then it will smear, when you look through it, all the intensities vertically. So if you have the time now, maybe stop the video, go to your kitchen shelf and find a wine glass, and then try to put this rod that holds the wine glass horizontally. So you're tilting the wine glass, put it horizontally, so the glass would sort of be like this here, yeah, and you look with your eye directly through this rod. Then that should smear all the intensity signal in the y direction, so in the vertical direction. And this smearing will give you then an impression, or really an overlay of all these intensities, and you should be able to see something that looks like this here. So you see, this is a nice sort of demonstration that by adding enough sine waves, you can get a signal that looks much more rectangular. So this is, of course, what we want to represent. And because we have only positive signals, we cannot get the constant right, but the rest is pretty good. So this way, we want to represent a rectangular grating, but we can represent it as a sum of sine waves. So this is an experimental way of performing a one-dimensional Fourier transformation. Of course, we can also do the same game with other things. So this is an asymmetric ramp, like a sawtooth signal, and you can also represent it by adding up a couple of sine wave components, and you should see something like this middle picture here when you do the same trick to this picture, and I'm going to show you a next one. So this is the sine waves arranged in such a way that they have all equal strength, and that means that we are trying to represent a delta sort of grating, which is of course particularly difficult because you see these are very narrow bars here, and we would need many more components like shown right here now. However, you get the impression that we have already a lot of small peaks on a background here, and so we're getting closer to these delta comp, as it is called. So now these were all periodic signals, but we are really representing objects that are typically not periodic. So what can we do to represent non-periodic objects? Well, we go from a Fourier analysis to what is called a Fourier transformation. This would require infinitely many frequencies to add, but the same concepts hold. However, if we do this in a computer, then what you simply do is you have a certain field of view of your image, and you're representing, you're really performing a Fourier analysis of this whole thing as a periodic function, but you make this object periodic artificially. So that means if you have one picture, let's say we are Fourier transforming Mr. Fourier, you really place him on a periodic grid like this. So this is called a digital Fourier transform, and it gives you certain artifacts, but it gives you an approximation of the real mathematical Fourier transform that would be an infinite sum of sine waves. So here we are. That's Fourier as a periodic extension of himself, and we then Fourier transform him, and we have now certain spatial frequencies. And what you see on the right is the representation of this Fourier transform in terms of the amplitude strength. That means every pixel, the brightness of every pixel relates to how strong of a wave you need to do this. However, what it doesn't show you is the second part, a hidden information that in the original Fourier transform represented as a complex valued thing, would be in there, which is the phase of the wave. And it turns out that the phase is actually more important than the amplitude information. So it shows you precisely this. Let's say if you represent it with a bright, dark, bright sine wave, then it's very important that the dark part is in the middle and not at the side. So the where information is represented in the phase, whereas the how much information is represented in the amplitude. So now what does it really mean? Well, I'm sort of zooming in and showing you the examples. So when we have a very coarse Fourier transform, a pixel somewhere here, it would give you a wave that is very coarse, going bright, dark, bright in this particular. So it's in this case 1 frequency per image. Then the next one would be 2 oscillations per image. And the next one 3, and so on, 4. And then the finer you go, the further out you go from the middle point, the finer the frequencies it corresponds to. Of course, when we choose a point that is not on one of these axes, then it would start to be a wave that is oriented in a different direction. So basically the vector here to this point represents the orientation of the wave. Again, if we go further away from the middle, we keep the orientation, but we make more periods. So higher spatial frequency in terms measured in terms of oscillations per meter. So what this shows you is sort of a graphical representation of showing you that we can really decompose anything into sine waves. And so what you see here is the opposite. If you want, it's called a Fourier synthesis. So I'm showing you how to make a picture from summing up waves. And what you are going to see is 4 panels. On the top left part, you see the current spatial frequency that we are looking at. On the top right part, you see the current real space sine wave that we are representing currently. On the bottom left part, you see the accumulated frequencies. So that is all the frequencies we have so far taken into account. And on the bottom right part, you see the sum of all these waves, all these sine waves, when they are summed up in real space. And I will show you a video then that shows you how by adding more and more sine waves, we're getting closer and closer to our picture. So the first, of course, the 0 frequency, as you've learned before, just represents the average value. So that's why you see an equally gray value. It's unfortunately shown as white here. It should probably be a little bit darker, grayer. So that's a gray value, which is just the average of the whole image. And if we synthesize this, that's pretty boring. That's a constant. However, the first sine wave corresponds to something like this. So if this was the first really the lowest frequency that we can represent being 1 pixel here, well, first of all, because Fourier transform is a complex valued thing and we have real valued images, we always get actually 2 frequencies, one at plus k and one at minus k, because if you have e to the ikx plus e to the minus ikx, you're basically, well, divided by 2, you're getting a cosine wave like you would be getting here. And then depending on what phase they really have, you can shift this wave around. So that's represented here. What you might notice, if you're really looking closely, that this is not 1 oscillation as you would expect, but it looks like 2 oscillations. The problem is that I accidentally actually plotted here on this top right part, I plotted the absolute of the wave. That's why when it goes negative, like it would be doing here and here, then it looks like it's positive. So sorry for that. But you see, actually, when I'm adding up the original constant plus this wave, it really does just 1 oscillation going from dark, bright to dark again and starting to get brighter here. So now when we add another wave, you see now this has more oscillations. So this would be 2 oscillations per image and so on. We're adding more and more and more at higher and higher spatial frequencies. If we finished adding a whole line like I'm showing you here, then that gives you basically only information along the y direction. So you get some sort of patterning along y, but nothing along x. If we then have added the whole, the whole thing, but we added already the first component in the x direction, you see now we start getting also features in this direction. So the first oscillation being negative, positive, negative here is also shown. and so on. We add diagonal 1, and now you will see a video in a second that by adding all the components, you're starting to actually reconstruct an image. You see how more and more of a feature can emerge. You start to see a smiley face here, and when we filled all the frequencies, we've actually represented our image up to that maximum possible frequency, which interestingly would be the diagonal frequency up to the corner here, the highest frequencies we can. We get our smiley face. So now you can imagine that it is possible to have any combinations of pixels and basically represent them as a sum of spatial frequency patterns in 2D, and in fact even in 3D or 4D or whatever you like. So why is that important? Well, remember back, we were talking about optical transfer function in the picture in Fourier space and point spread function, the picture drawing with the brush operation convolution in real space. And of course, this is what's going to happen in Fourier space. We have some pictures. So this is the Fourier transform of Mr. Fourier shown here. And when we start to cut away frequencies, so this is our optical transfer function as a radial representation, we cut away the highest frequency, that looks still pretty fine. But when we cut more away, like shown here, then you see that Mr. Fourier starts to get more and more blurry. So because we're deleting the high frequency information, it's equivalent to fluffing him with a more coarse brush. This is a brush with lots of side lobes, as you can start to see. And you see the more we cut away, the more blurry he becomes. So where a point here is, it's a dark fringe, and that's because we actually cut it away very, very sharply. We can ameliorate that a little bit by having a more triangular decay, as shown here. And you see it looks like most of the fringes are gone. If you really measure this, there's still some fringes there, and it turns out you can never get the fringes really to be going away, but you can make it such that the total result never becomes negative. So this is what we have here, and then we can play around and we can maybe make an anisotropic filtering, as this is called Fourier filtering, and that's what a microscope does. You can say a microscope is a Fourier filter. It cuts away frequencies in Fourier space and it dims down other frequencies. So this is asymmetric, if you want, or anisotropic. We are cutting away a lot of information in Y, or here it's called Z, because that's what a microscope often does, like a confocal microscopy, pretty much like this, has a bad resolution in Z. This means a small distance in K space here, a good resolution, lots of K frequencies in X. So you see this here, for example, his collar is really still very sharp compared to his shoulder, which is blurred in Y very much because the collar is oriented such that it's pretty much it's the same shape in Y direction, whereas this shoulder isn't, and therefore there's a lot of blurring in this direction, very little blurring in this direction. But of course, you can do other shapes, like something like this. So low frequencies are cut a lot, then in the middle they are not cut so much, and then again at high frequencies they are cut. And if you do this, then you can actually mimic how an XZ stack of a wide field transfer function would look like. And indeed, this looks very much like what you see here. So here you see a representation of the effect that an optical transfer function has on an image of a periodic object. This could be a sine wave. It could also be any other periodic feature. And you see that if we have in the object a very coarse period, that you get an almost perfect image of that coarse frequency, as it is not dimmed down a lot. So the contrast is really pretty good still. However, if we have now a finer frequency, the effect of the microscope blurring is that the contrast is less because it's smeared more into each other, so to say. Interestingly, it always remains a sine wave here. And at a certain point, and that is of course the Abbe limit, we have a certain frequency where this becomes zero. It becomes exactly zero, And interestingly, from there on, even higher frequencies become exactly zero. So in some way, this is a very non-trivial thing that there is this absolute frequency limit and there is no more aliasing going on. The higher frequencies are dimmed down to zero, and that's a particular property of wave-like imaging systems, that there is such a fixed frequency limit where nothing is transferred. Why is it a constant? Because of course this is not a sine wave, it's an intensity pattern, so I had to always add a constant to it. It's a sine wave plus a constant, and therefore the constant always gets transferred perfectly. It remains there, and the sine wave is deleted completely. So the same is shown in the next slide here, and you see coarse sine wave, again, coarse protocoled as a pretty good contrast. Smaller sine wave, less contrast, put down like this here. Abbe limit, zero contrast. And higher frequency, also zero contrast. So in total, you have a transfer function that shows you now how much is transferred. So I think now you understand really what is the meaning of the optical transfer function.